All right, so the next talk is one of the award papers. I noticed they scheduled them against each other, so you had to decide which award paper you wanted to see this morning. So Mohammed is going to give us a talk on edge caching. He's a fifth-year PhD student at EPFL, where he's advised by Katerina. So.
Thank you for the introduction. Hi, everyone. My name is Muhammad Abdullah, and I think these are the wrong slides. I can present this. How do I change? Okay.
There we go.
Okay, welcome back. So hi, everyone. My name is Muhammad Abdullah, and I'm a PhD student at EPFL, and I'll present our paper titled Edge Caching as Differentiation. This is a joint effort with my excellent colleagues at EPFL, Mugiz Pavlos, and my PhD advisor, Katerina Argiraki. Whoops. Yes. Okay. So what is traffic differentiation? Nope. It's working now. What's happening? Okay, I'll just use the keyboard. Okay, that's fine. Okay, so what is traffic differentiation? It is when a network does something that causes an end user to experience one piece of online content with better quality of experience, or QoE, and another piece of online content with a worse QoE. Typically, when we say traffic differentiation, we have a setup like this in mind, where a network has different queues and it prioritizes traffic for one content, causing the user to experience the other content with worse QoE. However, these days, a different reason why users might experience online content with different quality is edge caching. And how so? Consider a scenario where a network does not do any explicit prioritization, and instead it hosts an edge cache from a content delivery network, or CDN. And user watches videos from two different video streaming services, A and B, both of which are customers of the CDN. They have the same kind of contract with the CDN to host or cache their content on its edge caches. Now, if A is much more popular than B, then naturally, service A would achieve much higher cache hit rate than B. So for example, if A has a hit rate of 99%, that means that 99% of the requests for service A would be delivered directly from the cache, resulting in faster response time and thus better QoE, as opposed to B, where the request would have to go all the way to the origin server, resulting in slower response times and thus worse QoE. Now, this is also a form of traffic differentiation. It is not intentional, it's not malicious, but it happens because of the dynamics of shared caching. Now, if you're thinking, does a big difference in cache hit rate cause a big difference in the QoE? And to answer this, I'll show you results for two real video streaming services that we actually measured. One with a high hit rate of 99%, and the other with a hit rate of just 40%. When we measured their videos from our client, we observed that on average, videos from service B took 2.5 seconds longer to start playback. And based on a popular study by Akamai, this additional delay can translate to roughly 30% users abandoning the video. Moreover, on a client with low bandwidth connection, we found that on average, videos from service B froze 2.8 times in 1 minute of playback, as compared to just 1 time for service A. And based on a study from Columbia on YouTube videos, multiple rebuffering events can increase abandonment to 3 times. And finally, we also observed that videos from service B had 20% lower playback quality on average than videos from A. So in summary, we have two streaming services, both customers of the same CDN, and yet they achieve very different hit rate, and thus users experience them with very different QoE. Now, some of you might think service A achieved much better cache hit rate because it paid the CDN more than B. Well, it is possible, but unlikely. And I will explain this in CDN pricing later on in the talk. And some of you might think, what's the big deal? A is so much more popular than B, so of course it's going to enjoy much higher hit rates than B. And it makes sense that a more popular service enjoys better caching performance. But 20 years ago, if a network did something that caused users to experience a popular service with much better quality than its competitors, it was a scandal. And there was this strong perception that a network should not do anything that would give competitive advantage to big established players. We used to talk about this back in the day. Maybe we should now too. So the key question that we try to answer in our paper is, how large are the QoE disparities caused by caching? And are they prevalent around the world? Now, before I share you our answers, let's first look at typical caching hierarchy in CDNs. So closest to the user at the edge, there are layer 1 or L1 caches. Behind those, we have larger L2 caches, and behind those lie the origin server. So a service with more L1 cache hits would perform better than a service with more L2 cache hits, and that would perform better than a service with more cache misses. Now, in order to see the QoE disparities caused by caching, we conduct a large-scale measurement study where we collected data from 8 different locations around the world, covering 5 major CDNs and over 25 different video streaming services. And in our data set, we had L1, L2 hit rate, as well as latency, measured across a period of 30 days, and that amounts to about 30 million different measurements. So to collect a measurement, we have a web crawler that looks at top 100 most popular videos from a streaming service. And for each video, it extracts its manifest file, which contains the URLs of all of its video segments. And during peak streaming hours, we probe each video segment using a lightweight HTTP head request. And based on the HTTP response headers, we determine whether that segment was cached or not. And we also record the time of the latency of the response. And by stitching these two together, we create a latency trace for each video, which contains information about latency as well as cache hit status of each video segment in that video. Now, if you're curious, how do we deal with the effect of network congestion or how we determine video popularity, I'm not going to go into their details, but you can read that in the paper. Now we have the latency trace. The next step is to translate that into video QoE. And to do that, we feed these latency traces into Sabre, which is an open source video player that simulates playback to compute realistic video QoE metrics. Now, we all know QoE, or playback quality of videos, do depend on so many factors. For instance, the network bandwidth of the client, the original quality and content of the video, as is described in the manifest file, the ABR algorithm used in the video player, and the size of its playback buffer. So in order to isolate caching's true impact on QoE, we eliminate these dependencies by using same reasonable parameters for all videos when we feed their trace into Sabre. And on top of that, we also fix the miss latency value. Why? Consider this example. Video A has origin server 1 continent away from the client at 300 milliseconds, whereas the origin server for video B is multiple continents away at 900 milliseconds. And so even if both videos have the exact same cache hit rate, B would perform worse just because its origin is much further away. So to fix this bias, we replace the cache miss latencies by a fixed value. And what fixed value exactly? We pick the fixed value from the distribution of miss latencies that we actually measured. And specifically, the mean values of the 3 clusters we see in the distribution. The first cluster happened to correspond to those video streaming services that had origin within the same continent as the client, whereas the next 2 clusters correspond to those origin servers that were 2 and 3 continents away from the client. So basically, we create 3 different versions of each latency trace with 3 different values of fixed miss latency. And now with latency trace with fixed miss latency value as input and all the other parameters controlled for, the QoE computed by Sabre now depends only on caching behavior, specifically cache hit rate and the cache hit latency. And for video QoE, we consider a standard metric that consists of 4 components. And these components combine into a single metric, which is basically the video bitrate, penalized by the weighted sum of other components that negatively affect user experience. And in the paper, we call this adjusted bitrate. Now let's look at some of the results. So this scatter plot shows L1 and L2 hit rates of video streaming services that our client measured in Indonesia. So on the x-axis, we have CDNs or caching provider with anonymized names, P1 and P2, and each data point shows one streaming service, specifically its average value. And just by looking at the plot, we see big differences in the hit rate. Let's focus on P2. So in P2, the most cached service had an average L1 hit rate of 99%, and for the least cached service, it was only 34%. So now how does this difference translate into QoE? With a client bandwidth of 25 megabits per second and miss latency set to just 62 milliseconds, cache misses have little impact on QoE. But as we increase the miss latency, the differences become much more significant. At 370 milliseconds of miss latency, the least cache service had 10% lower average adjusted bitrate as compared to the most cache service. And at 900 milliseconds of miss latency, this difference was 33%. And we see these differences and even bigger differences in all locations around the world where we had set up our measurement client. For example, at 900 milliseconds of miss latency, the difference between the least cache and the most cache service was 29%, 41%, and even 50%. So since this adjusted bitrate is an aggregate metric, so I will focus on one of its components that we can all intuitively understand, and that is the startup delay. So videos from least cache service took 2.5 seconds, 3.5 seconds, and even 4.5 seconds longer to start playback as compared to videos from most cached service. In the paper, you can find even more results. So in the start of the talk, I promised that I will get back to CDN pricing. So here's how it works. Basic pricing is common for all customers, meaning they pay the same per byte requested from the cache, plus an additional miss tax for fetching data from the origin as a result of a cache miss. So that means that less popular services actually pay more because of this miss tax. And obviously, this creates an extra challenge for newcomers. And on top of that, CDNs also offer additional features. For example, customers may choose the location of L2 caches and in some cases reserve space in the L2. However, there is no such service available for L1 caches. The customers cannot pay CDNs to get a guaranteed L1 hit rate. And so naturally, more popular services attain higher L1 hit rate, and so most QoE disparities can be explained from popularity. Now, some of you may think that the reason behind the disparities could be private deals that CDNs may have with customers. We don't have evidence to support this. They may exist, and if they do, we think that is bad for competition. And before I move on to conclusion, I want to make 2 things very clear. First, we are not asking for regulations for CDNs or caching, and we're not claiming that caching exists only for performance. The primary role of caching is to reduce cost, to reduce the amount of traffic that goes to the origin server. But that does not change the fact that caching causes disparities in QoE. And this plot summarizes our findings. It shows adjusted bitrate or QoE as a function of miss latency. So the curve at the top in red shows QoE of content that is 100% cached. So it appears as a flat line, unaffected by mislatency, whereas the bottom curve in blue shows QoE for content that is not cached at all. So it's most affected by mislatency. And the gap between these two QoE curves show potential competitive disadvantage that an unpopular service can face. And this gap widens as mislatency grows. So some of you might think that with the passage of time and with better internet connectivity, mislatencies would reduce and the QoE gap would diminish. But a more pragmatic expectation is that with time, our definitions of QoE and users' expectations will also change. And so we expect that the gap between cached and uncached content will most likely always exist. So what do we want our community to do with this? First of all, we want to keep track of such type of QoE disparities and how they evolve with time. And secondly, should we revisit public caching? And should we revisit caching strategies that take QoE into consideration? And I'll conclude with these two questions. Thank you.
Time for some questions.
Thank you for the fabulous talk, Marwan Cloudflare. So this is really fabulous. Why should it only be popularity and not diversity alongside? So I can imagine I'm a less popular service, but I have less diversity of content, and so my stuff is more likely to be cached than the very popular service that has more content.
Right. So in the result that I showed, we measured average L1 and L2 hit rate taken from the top 100 videos. So for example, if we take more videos, the results would change depending on the individual popularity of each video, but we take the average.
Hi,
Yeah.
Great talk, thank you so much. I have a question. So it seems that the conclusion is the cache misses or unpopular contents would have less advantage in CDN, so that's why we have worse QoE, right? But you did mention some strategies moving forward. Could you explain some of the thoughts? How can we make that change? Or do you think this is fair, kind of, if your content is unpopular, while it becomes by natural, you know, it has to be.
I see. So in terms of fairness, I think this is for the policymakers or regulators to decide whether this is fair or not, or what, if there's any need for new laws to regulate this sort of behavior. But in terms of strategies, an unpopular service would have to innovate in other areas in order to get at the same level as the popular services. So for example, when I talk about QoE-aware caching, one way that could be done is like giving a threshold caching to unpopular services so that they can compete with the established player. This is one way, but this is an open question, so it's up to the community to see what can be done.
Yeah, maybe it's another way to ask Marwan question. I'm here.
Okay.
I didn't really get the notion of popularity, because you talk about popularity of the service, how you measure it, right? So there is, if there is some service has a lot of unpopular videos, it's one thing. Another is just, have a small number of videos, small number of customers. So what's the definition of popularity?
So two streaming services, like the difference in the popularity, we get that from the number of daily visits that they receive, and the data is available online. But each video can have like different popularity, right? But since we are taking the top 100 most popular video, we're considering the best case. So for example, if two services, in general, there is a difference in popularity, we are measuring the best videos from both of these services, and the results explain the difference in the QoE.
And maybe just quick follow-up question is, again, you said you don't argue for regulation, but at the end, what's the point, right? So if you don't argue something like net neutrality for this, it's just for information, or you really want to push some solution where, everybody gets equal service regardless of popularity?
I see. So basically did what researchers do. We present numbers, we present what's happening on the internet, and now the ball is in the court of the policymakers and the regulators to decide what they want to do with it. But we're just presenting numbers, and we're showing that these differences exist, and the differences are significant.
All right, let's thank the speaker one more time.